All right, we're still in section 3.4, going through finding the real zeros of a polynomial function. And in this video, we're going to be focusing on two things: Descartes' rule of signs, as well as the bounds on zero theorem, both of which can be used to help us narrow down our possibilities for the real zeros of a function, okay? All right, so first thing we want to recall is that a polynomial function cannot have more real zeros than its degree, okay? So for example, if the degree of your function is 6, then your function cannot have any more than 6 real zeros. It can have fewer than 6, but it can't have more than 6, okay? And notice down at the bottom here, I have a note that multiple roots count as multiple zeros, okay? So let's say I have one root that has a multiplicity of 2. That means I have to consider that root twice when I'm adding up my total number of zeros, okay? So in the situation of the degree being 6, if one of the roots has a multiplicity of 2, then that means that I can only have 4 other roots, 4 other unique roots whose multiplicities are each 1. Okay, so just kind of keep that in mind as you work through the examples here today. All right, now Descartes' rule of signs. Okay, this is a rule that allows us to determine how many positive zeros and how many negative zeros our function might have. Okay, there's two parts to it. So obviously we're working with a function f. It has to be written in standard form, okay? And in the first part, we're focusing on the positive zeros of the function. It says that they will equal the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer, okay? So I'll break that down for you as we work in an example, okay? I know reading it might seem a little confusing, okay? Um, the second half of the theorem focuses on the negative zeros of the function, and it's essentially the same thing as the first half, except now you would be looking at the number of sign variations in the non-zero coefficients of f of negative x, okay? So let's just get right into an example to help you see how this all works, okay? Um, Part A here discuss the real zeros of the function f of x there. So first of all, I'm paying attention to the degree of the function. It is 6, which means there could be up to 6 real zeros of this function. 6 real zeros of this function, okay? And next I want to look at the number of sign changes in the coefficients from term to term in f of x, okay? So what I mean by that is right here, there is a sign change. The first coefficient is 3, the next coefficient is -4. So you go from a positive coefficient to a negative coefficient. So right there's one sign change or one sign variation. Here's a second one, a third one, and then a fourth one. There is no sign change in the last two terms since they're both positives, okay? So that means there are 4 sign variations in f of x. So Descartes' rule of signs says that there could be 4 positive zeros to the function, okay? But then there's also, if we go back here, it says, or else equals that number less an even integer. So what we mean by that is this value of 4 that we've come up with, if it can be subtracted by any even integer and still result in a whole number, then that's a possibility for the number of positive zeros as well. So I could subtract 4 by 2, right? 2 is an even integer, and the result is 2, a whole number. So there could be 2 positive zeros as a possibility as well. Or I could subtract 4 by itself, right? 4 is an even integer. 4 minus itself would be 0, which is still a whole number, okay? So those are the possibilities for the number of positive zeros. Now we focus on finding the number of possible negative zeros. That requires us to find f of negative x for the function, okay? So for this function, f of negative x would be as follows. Don't overcomplicate this. Basically, f of negative x, you're just going to end up changing signs on the coefficients from the original function that were coefficients on variables whose powers were odd numbers, okay? So notice when you compare f of x with f of negative x, these are the only terms right here and right here whose signs on their coefficients change. That's because when I raise negative x to an odd power, it's going to stay negative, okay? All right, now we look at sign changes in this function, right? There's one sign change, and then we don't get another one until the last two terms. So that means we have two total sign variations in f of negative x, so there could be two negative zeros, or 2 subtracted by itself, because it's an even integer, means there could be 0 negative zeros, okay? So now kind of, put this all together. What this is stating, these results, your function has the potential of having maybe 4 positive zeros and 2 negative zeros for a total of 6 real zeros. Or maybe it could have 4 positive and 0 negative, meaning there would only be 4 real zeros and the other 2 would have to be complex. Or it could have 2 positive and 2 negative for a total of 4 real, which would mean the other 2 are complex. Or there's a bunch of combinations where you could only end up with 2 real zeros. So you could have 2 positive and 0 negative, or 0 positive and 2 negative. That would mean the other 4 would have to be complex. Or the last possibility is you could have no real zeros, 0 positive, 0 negative, which means all 6 would have to be complex. Okay? Let's drive this home with a second example. So in part B, the function f of x has a degree of 2. Okay? And that means there's going to be up to 2 real zeros. There are no sign variations in f of x. Each term has a positive coefficient. So if there's no sign variations, then there's no positive zeros to this function. Okay? So right there, you just cut the number of possibilities in half in the real number system. Okay? How about f of negative x? It would equal x squared minus 6x plus 9. So right there's a sign change. Right there's a sign change for a total of 2. That means you could have 2 negative zeros, or subtracting 2 by itself, since it's an even integer, you could have 0 negative zeros as well. So basically what these results are stating is that if this function has real zeros, they both have to be negative, okay? If they're not negative, then they're both going to have to be complex, okay? All right, now we move to bounds on zero theorem. First, let's talk about a bound. A number m is a bound on the zeros of a polynomial if every zero lies between negative m and positive m. So if I said that m equals 5 is a bound on my zeros, then that means all the zeros of that function would have to be between 5 and negative 5, okay? Having a bound is beneficial because, again, it just kind of narrows down the number of possibilities for the real zeros of your function, okay? So the bounds on zero theorem helps you find a bound for your function, okay? In order to use the theorem, your function f has to have a leading coefficient of 1, okay? So it has to have that as a 1. All right. If it doesn't, we can fix that pretty easily. And then what the theorem says, it's got 2 parts or 2 formulas to it. So the first formula will be right here, and Notice it's got this notation. It's got a max with a brace and then a bunch of stuff inside the brace, okay? So basically what that max notation means is it wants you to choose the largest entry within the braces, okay? So what the first half of this formula is going to do is it's going to have you compare the number 1 with the sum of the absolute values of a sub 0, a sub 1, all the way up to a sub n in your function, okay? So basically what that's stating is add up the absolute values of all of the coefficients on these terms of the function, okay? Notice you're not including the leading coefficient in that. And when you add all those up, you're going to compare that value with the value of 1, and whichever one is largest, that's the one you're going to choose, okay? Now the second half of the formula is over here, and notice it looks very similar, yet it's very different from the first one. Now the 1 is moved to the outside of the braces, and now you're adding it with the largest entry between the absolute value of a sub 0 compared to a sub 1 all the way up to a sub n minus 1. So notice those coefficients, their absolute values aren't being added together anymore. Instead, you're comparing them separately, and you just pick the biggest of those and then add it with the 1 out in front, okay? Now, when you're all said and done, the formula I have underlined in purple and the formula I have underlined in green, they'll each result in a number, and of those two numbers, you are going to choose the smaller of the two. That number will be your bound, okay? So let's see the theorem at work here. Find bounds on the real zeros of this function f, okay? First thing I'm noticing, leading coefficient is not a 1. No big deal. I can fix that pretty quickly by just dividing everything out by that coefficient. And then I'm going to rewrite this. Instead of f of x, I use 0. I can replace it with a 0 since I'm talking about the zeros of this function. And I rewrite the right side here as x to the 4th plus x cubed minus 1/3 x squared minus 4x minus 4. Okay. Now I start my first half of the theorem. So the first half, its setup will look like this. I'll choose the largest entry between 1 and the absolute value of all of the coefficients in the function added together, with the exception of the leading coefficient. So I'm basically adding the absolute values of all of these terms' coefficients together. Okay, so that's going to result in the largest entry between 1 and 9 1/3. And of course, between those two numbers, 9 and 1/3 is larger. Okay, so you kind of hold on to that for a moment, and now you use the second half of the theorem. Its setup would look like this. 1 plus the largest entry between the absolute value of -4 compared to absolute value of -4 compared to absolute value of -1/3 compared to the absolute value of 1. So again, notice I'm not adding those absolute values together in the second half of this theorem. Instead, I'm comparing them all to one another. Out of those 4, the largest, once you take the absolute value, would be 4. So this is going to become 1 plus 4, which gives me 5. Okay. All right, now you take the two results of 9 and 1/3 and 5, and you ask yourself this question. Which of those is smaller? Okay. Which of those is smaller? So the obvious answer is 5, right? That means m equals 5 is the bound. So all zeros of this function, f of x, all real zeros, let me add that in, all real zeros of f of x will have to fall between -5 and +5. Okay.